Projectile motion, Part 2, components and maximum height. Quick recap before we start calculating. Ux equals Vi cosine theta, and it stays constant the whole flight. Oi equals Vi sine theta, and it changes every instant, because gravity pulls it down. Today we calculate. Let's start with a step-by-step method for finding Ux and Oi. First, identify Vi, the initial velocity, and theta, the angle of projection, from the question. Second, write down the formula, Ux equals Vi cosine theta, Oi equals Vi sine theta. Third, substitute the actual numbers into that formula. Fourth, evaluate cosine theta or sine theta as a decimal. And fifth, multiply through to get the final answer, always in meters per second. Example 1. A ball is launched with an initial velocity of 20 meters per second, at 30 degrees above the horizontal. Let's find its horizontal and vertical velocity components. Here's the launch, at 30 degrees. Watch it split into a horizontal part and a vertical part. The horizontal component, Ux equals Vi cosine theta. Substitute in, 20 times cosine 30 degrees. Cosine 30 degrees is 0.8660. 20 times 0.8660 gives Ux equals 17.32 meters per second. The vertical component, Oi equals Vi sine theta. Substitute in, 20 times sine 30 degrees. Sine 30 degrees is 0.5000. 20 times 0.5000 gives Oi equals 10.00 meters per second. Example 2. A ball is launched with an initial velocity of 50 meters per second, at 45 degrees above the horizontal. Let's find its horizontal and vertical velocity components. Here's the launch, at 45 degrees. Watch it split into a horizontal part and a vertical part. The horizontal component, Ux equals Vi cosine theta. Substitute in, 50 times cosine 45 degrees. Cosine 45 degrees is 0.7071. 50 times 0.7071 gives Ux equals 35.36 meters per second. The vertical component, Oi equals Vi sine theta. Substitute in, 50 times sine 45 degrees. Sine 45 degrees is 0.7071. 50 times 0.7071 gives Oi equals 35.36 meters per second. Example 3. A ball is launched with an initial velocity of 25 meters per second, at 60 degrees above the horizontal. Let's find its horizontal and vertical velocity components. Here's the launch, at 60 degrees. Watch it split into a horizontal part and a vertical part. The horizontal component, Ux equals Vi cosine theta. Substitute in, 25 times cosine 60 degrees. Cosine 60 degrees is 0.5000. 25 times 0.5000 gives Ux equals 12.50 meters per second. The vertical component, Oi equals Vi sine theta. Substitute in, 25 times sine 60 degrees. Sine 60 degrees is 0.8660. 25 times 0.8660 gives Oi equals 21.65 meters per second. Now, maximum height. Let's not just state the formula, let's derive it from first principles. Consider only the vertical motion, straight up, like a ball thrown upward. At launch, the vertical speed is Oi equal to Vi sine theta. As it rises, gravity slows it down, the vertical speed shrinks. And at the very top, the peak of the flight, the vertical velocity hits zero for an instant. This is the moment of maximum height. Start with a standard equation of motion, v² equals u² minus 2gs, here u is oi, the vertical speed. At the peak, the vertical velocity v is 0, and the distance risen, s, is the maximum height, h. Now substitute oi equals vi²sin²θ, the formula from section A. Squaring that out, vi² sin²θ. Rearranging, move the 2gh term across to the other side. And divide both sides by 2g. That gives us the maximum height formula, h equals vi² sin² over 2g. Example 1. A projectile is launched with an initial velocity of 30 meters per second, at 60 degrees to the horizontal. Let's find the maximum height it reaches, taking g equals 10. Watch it rise to its peak, launched at 60 degrees. Start with the formula, h equals vi² sin² over 2g. Substitute in the numbers, 30 squared, sin² 60 degrees, over 2 times 10. Evaluate, 30 squared is 900, and sin² 60 degrees is 0.7500. The denominator is 20. Multiply the numerator, 900 times 0.7500 is 675.00. Divide by 20, the maximum height is 33.75 meters. Example 2. A projectile is launched with an initial velocity of 40 meters per second, at 45 degrees to the horizontal. Let's find the maximum height it reaches, taking g equals 10. Watch it rise to its peak, launched at 45 degrees. Start with the formula, h equals vi² sin² over 2g. Substitute in the numbers, 40 squared, sin² 45 degrees, over 2 times 10. Evaluate, 40 squared is 1600, and sin² 45 degrees is 0.5000. The denominator is 20. Multiply the numerator, 1600 times 0.5000 is 800.00. Divide by 20, the maximum height is 40.00 meters. Example 3. A projectile is launched with an initial velocity of 25 meters per second, at 30 degrees to the horizontal. Let's find the maximum height it reaches, taking g equals 10. Watch it rise to its peak, launched at 30 degrees. Start with the formula, h equals vi² sin² over 2g. Substitute in the numbers, 25 squared, sin² 30 degrees, over 2 times 10. Evaluate, 25 squared is 625, and sin² 30 degrees is 0.2500. The denominator is 20. Multiply the numerator, 625 times 0.2500 is 156.25. Divide by 20, the maximum height is 7.81 meters. Let's recap the two formulas from today. Ux equals vi cosine theta, the horizontal component, which stays constant. Oi equals vi sine theta, the vertical component, which hits zero at the peak. And h equals vi² sin² over 2g, the maximum height reached. Here's one for you to try. A projectile is launched at 35 meters per second, at an angle of 50 degrees, taking g equals 10. What's its maximum height? Work it out, and drop your answer in the comments below. Next time, in part 3, time of flight and range. See you there, on the Concept Lab.